Yuriy, we'll just or something to don't want to start too early, but you can put it onto full screen mode. Great. Okay. All right. I think now, please give us your talk. Just on mute still, Susan, so we're not hearing anything.
Yeah. Can you hear me? Okay. Can you hear me?
Yes. Not super loud, but yeah, we can hear you. Yeah.
Oh. Good day, everybody. This talk is devoted to the nonlinear interaction between continuous ice sheet and the fluid perturbed by abstraction on the bottom. This problem has many industrial applications, offshore and polar engineering, medicine, etc. The problem of interaction between ice sheet and water waves is a classical problem of fluid dynamics, and it is quite challenging from mathematical points of view. Most of publications to the present are based on the linear theories of the water waves and the theory of a semi-elastic shell modeling the ice cover. One feature of the problem is various types of the response of the ice sheet, which depends on the velocity of the wave propagation. The linear theories are applicable to derive the dispersion relation. However, they are restricted to consider waves of small amplitude. The number of papers devoted to the nonlinear hydroelastic interaction are very limited. We mention here the paper Parao and Diaz, 2002, where the effects of nonlinearity are studied at speeds slightly below the minimal wave speed. They derived a nonlinear Schrödinger equation, presented weakly nonlinear analysis, and computed and compared the results with the fully nonlinear computation. Computation of nonlinear waves is a challenging task. Bonifoy et al. Developed a higher order spectral method and calculated the nonlinear response of an infinite ice sheet to a moving load in the time domain. Guillaume and Parao discovered depression and elevation branches of solitary waves below the minimum of the phase speed using Casserat's theory of hydroelastic shells. Page and Parao investigated trapped waves between two abstractions using boundary integral method. Then Guillaume and Parao developed a numerical method and investigated integration of solitary waves in fragmented ice sheets. In the recent paper by Yuriy and me, the nonlinear gravity waves in the channel covered by broken ice were investigated. In this talk, we extended this solution to the problem of continuous ice sheet. Formulation of the problem is presented in this slide. We consider steady flow in the channel with abstraction and introduce a complex velocity potential. The apparatus of complex variables has advantage. We don't care about the solution of Laplace equation because the real and imaginary part of complex function satisfy the Laplace equation, any complex function. What we have to do is only to find such a complex function which satisfies the given boundary condition. Bernoulli equation is written on the interface, Here, P ice is the pressure on the interface from the liquid, and it is equal to the pressure providing the balance of the elastic sheet. It will be shown later that there is a flow regime for which two waves of different wavelengths may exist. This wave may extend to infinity, but for computational purpose we need to have a uniform flow at infinity. This can be provided by adding the damping term in the dynamic boundary condition. The coefficient CD equals 0 in the calculation region of interest, and it is not 0 at the damping region. We use photograph method to determine the complex potential of the flow. Determination of function complex potential W on Z is a difficult problem. Therefore, Joukowsky and Mitchell proposed to introduce an auxiliary parameter plane or zeta plane. Then they proposed to search two functions, complex potential and complex velocity, both as function of the parameter variable zeta. If these functions are found, then their combination and integration of their combination, we can obtain mapping function which relates parameter of the physical plane and parameter plane. In the present case, for the channel flow, the complex potential plane is quite simple. This is just a strip, and we can immediately to find conformal mapping of the first quadrant onto the strip. This is just function logarithm, and its derivative easily can be found. To find the function of complex velocity, it is a more sophisticated problem. At this stage, we assume that we know the slope to the bottom, and we know velocity magnitude on the interface. It means we know the velocity magnitude on the imaginary axis of the first quadrant and the slope argument of the complex velocity on the real axis of the first quadrant. Then we apply an integral formula which solves this mixed boundary value problem. This formula immediately provides complex function which satisfies the boundary condition 4 and 5. What we need is to consider the slope has corner point ASC, and we have to evaluate the integral, first integral at this point, and finally can obtain expression for the complex velocity in this form. Then, as I was mentioned, combination of these two functions can provide mapping function. However, this function has logarithmic singularity. It means we have, if we use this formula, we have difficulties to compute parameter in the channel far from the origin at distances larger than 5 depths of the channel. To overcome this singularity, logarithmic singularity, we again come back to express the parameter variable zeta through the complex potential. And substituting this expression into the expression for the complex velocity, we obtain complex velocity as function of the complex potential. And finally, obtain derivative of the mapping function in the form 11. So it looks like Kirchhoff-Helmholtz solution, which they obtain its function dz also as function of the complex potential. This we can see this function has two unknown functions at this moment. Function slope to the bottom as function of the potential, and velocity magnitude on the interface also as function of potential. So to determine these two functions, first we have to consider shape of the bottom given by the slope beta ds is known function, and using the derivative of the mapping function, we can find a function d is the s spatial arc length coordinate along the bottom. So this leads to the integral differential equation shown here. Function d beta d phi appears in both sides, and its equation is easily can be solved using method of successive approximation. Also, we have two equations to determine position of point A and C. It can be found using this again this function of the S B on F. To determine the function of the velocity magnitude of interface is a difficult problem. If we proceed analytical derivation, we arrive to the hypersingular integral equation, which solution is quite difficult, numerical solution. So we go another way. We approximate the interface by spline, a spline of the order 5, which provides linear interpolation of the pressure between two nodes on the interface. So we can reduce, using the dynamic boundary condition, we reduce problem to the system of nonlinear equation in the nodes of the spline interpolation.
This is speaking is open.
And you can continue. Okay, we can obtain dispersion relation, is shown here. And in this dispersion relation, we can see three regions. First is subcritical flow, where there is no roots of this equation. Only in case of the without ice sheet, we have the solid line. It corresponds to the gravity wave. In case of the ice sheet, there is a subcritical flow region where there is no waves. Second region where there are two wave numbers in this equation, and we have two waves. First is the root is closer to the case without ice sheet, and we call this wave corresponding to this root as gravity wave. Second root is due to the elastic sheet, and we call it elastic wave. And in case of the channel supercritical flow, we can see one root, this equation has one root, which caused by the elastic sheet. To proceed to the results of computation, we verified the numerical algorithm, comparing the results with results of Page and Parao for the trapped wave, for the hydraulic fall and trapped waves between two obstacles. So solid line is a present solution, and solid circles is the results of the Page and Parao. We can see that it's completely results completely. One obstacle, in this case, rapid wave of two obstacles. Then we start to investigate subcritical flow regime, and we found that solution not always exists. Here, for each fruit number, there is some maximum height of the obstacle for which solution can be obtained. For example, for fruit 0.5, we found the solution maximum height is 0.32. In case we put value 0.33, we obtain this process of iteration. Process not convergent. In case of 32, process is well converged. So this maybe there is some physical reasons for such behavior of the solution. What is important is that as we approach to the critical ice critical fruit number, critical is 0.86. We computed 0.83, and this is maximum height of obstruction is 0.6. So height of obstruction and actually the deflection of the ice liquid interface decreases as we approach to the ice critical fruit number. The second region is the ice supercritical channel and ice supercritical channel subcritical flow. So we consider ice sheet thickness 0.05, to which correspond to the critical fruit number 0.69. And now we put results correspond to the fruit 0.9, which is quite closer to the critical value 1. And we can see the result deflection, bending moment, and pressure coefficient on the inlet. So we can see that the upstream deflection is very small, while downstream deflection is quite significant. And here two height of obstruction, the red line 0.5 and the blue line is 0.7. This is again maximum height of obstruction. Blue line corresponds to the maximum height of obstruction. The limitation now comes from the situation that local fruit number at the throw of the wave, is shown, the local fruit number shown by dashed line, and it becomes larger than critical value 1. So at the throw, flow became supercritical, channel super. And this is a limit, gives a limitation to get a convergent solution. Here we can see bending moment, and we can see that this contribution of the elastic shift also occur downstream, where at the throw of the wave we have some small oscillation corresponding to the frequency elastic wave. In case of the pressure coefficient, we clearly see oscillation caused by elastic shift. Upstream, in the upstream, and also we can see also deflection is very small. The bending moment upstream is about the same as downstream. Another is fruit number 485, and we can see amplitude of oscillation upstream somewhat higher. But again, we have limitation of the obstacle height of obstruction. Blue line corresponds to maximum height, and we can see again the local fruit number reaches critical value. The blue line. And here the again oscillation of the amplitude of oscillation of the bending moment upstream about the same as downstream. Also the amplitude deflection is quite small. And finally, when fruit number approaches to the critical fruit number, the wavelengths of elastic sheet and gravity wave approach one to other, and we have superposition of two waves of the closely wavelength. It well known from the theory of explanation. It causes quite complicated behavior. This superposition causes quite complicated behavior of the oscillation. Also, what we can see is that elastic wave decays downstream of the obstacle, but decays slowly as we approaches, more slowly as we approach the critical. Here is shown results for the channel supercritical flows. First, this case RA shown for the ice sheet thickness 0.05 and three fluid numbers 0.5, 3.3, 0.2. 0.2 is the lowest fluid number for which we can compute the results, and we can see that in this case the height crest increases, velocity on the interface decreases, and local fluid number go down and reaches subcritical value. So in this case, on the interface appear some waves, local waves, that make difficult to obtain convergent solution. According to dispersion relation, we have to see here some waves due to the elastic shift, but the amplitude is so small, so it's almost invisible. Also, we can see these waves in the behavior of the bending moment and pressure coefficient of the interface. As fluid number increases, the amplitude of oscillation decreases. Here shown the similar results, but for the ice sheet thickness 0.1, and we can see much more larger response of the ice sheet downstream. And again, the dashed line is shown the case of without ice sheet free surface, and we know that in case of free surface we have two solutions. First is perturbed wave, which is shown dashed line, and second is the soliton wave. We tried to compute a soliton wave in presence of ice, but we cannot obtain any convergent solution. Maybe it does not exist. But in case of perturbed wave, we have, in case of ice sheet, the boundary oscillate, interface oscillate near the perturbed shape of, near the shape of the perturbed wave. Here shown the dependence of the amplitude of oscillation as function of the ice thickness. We can see that there is a maximum of the deflection corresponding to about 0.3 and maximum pressure coefficient corresponding to about 0.2. Here shown region of existence, height fluid number between two critical fluid number, ice critical and channel critical. Solution can be obtained for quite small heteroreduction. Thank you for your attention.
All right. Just give a clap there. Sorry, I should have done that for Alex as well. You can clap there in the room, Sam as well. Thank you very much for your talk, but also for keeping so well to time as well. So, do we have any questions for Yuriy?
Someone will ask.
And Pete, please feel free again to write your talks, your questions in the chat. I've got some questions myself, but I'm just hoping that someone else a chance to ask. Yuriy, what's the main challenge compared to the case without the ice? When this method, the method's been developed for the case with just normal free surface. how does the ice make this more challenging? Maybe I'll write the question in the chat.
Yes, yes, it's completely true. In comparison with broken ice, we have more higher order of derivative which appears in the dynamic boundary conditions, and it makes additional computational difficulties. So in case of broken ice, we have third order derivative. In case of the continuous ice sheet, we have fifth order derivative. And as order higher than computation, we need more number of nodes to interpolate correctly, precisely the interface. That is main challenge.
But maybe ask another quick, slightly related question, but could you include the effect of compression in this? You know, this has become an interesting feature where we have compression, we get more wave modes appearing, or...
I hope, yes, I hope we can include the effect of compression with the dynamic boundary condition.
No, compression is actually it is kind of steady flow. So the role of compression is not effective here.
What compression?
Compression effective, but the result
here results without compression.
Without compression.
Yeah, but I think that you wouldn't have that supercritical. You could get weird things happening with the modes. Don't know how with that negative, those energy, you know. Yeah, it's just a thought.
No, sorry, I did not study actually effect of
compression.
No, I cannot answer precisely equation. But this method make it possible to include this.
What about the problem of a step? You know, there's another transformation that flattens. Do you know what I mean? The problem with a step that it goes like that.
Yeah, in point A and C we have corner points. These corner points we evaluated in expression 7. This is general formula for continuously changing of the slope, but in case of this step change, corner point is step change of slope. So we can easily evaluate this integral and obtain these terms for in point A and in point C. So this function, this function is continuous without any steps. It's just along the circle, along this semicircle. It continues.
But I'll take a risk and annotate. I was thinking of the problem where the bottom goes like that.
What bottom goes?
You know, we have a change in depth.
Change in depth, yes.
Yes, actually we can include any shape of the bottom. It's given by the function beta, and this is arbitrary function, and so we can investigate step bottom. Only the problem what we obtain at infinity. For example, if we have one step, just step, then we have, in case without ice sheet, we have a flow like hydraulic fall, with ice also. So condition if flow upstream subcritical, it will be downstream supercritical, and opposite. If supercritical upstream and step is increasing, then we obtain.
Yes, no, Yeah, that's right. The flow would have to change. So maybe if it was a wave or something. I think we should stop there though, Yuriy. I think it would be good. Thank you very much for your talk, and again, and thanks very much for the answering the questions.